Well, in previous sessions, we talked about some concepts related to electronics and also became familiar with the concepts of electric current and voltage. Now, in this session, we want to talk about what direct current and alternating current are, introduce you to these two types of current, so to speak, and see what characteristics each of them has. Well, here we have a comparison between direct current and alternating current. First, I'll give a brief explanation about each one, and with the explanations I provide, you'll definitely understand what differences they have. Of course, let me mention that this session is just a brief introduction and overview of these two types of current. In future sessions, when we delve deeper into electronics topics and start working hands-on, we'll engage much more with these two types of current, and at that point, we'll understand them much better and more deeply. But I thought it was necessary for us to have an introduction beforehand so that your mind is prepared for this topic. An electric current that continuously flows in one direction is called direct current or DC. DC is the abbreviation for the English term direct current, where the first letters of these two words are put together and pronounced as DC. It is known as direct current or DC current. And well, in the session about electric current, we saw that if we guide electrons in one direction, we have a current that we call electric current. So now, based on this definition, we can also say that an electric current that continuously exists in one direction without interruption or change of direction is called direct current. The electrons in a wire carrying direct current can be seen moving slowly through the wire, but ultimately they travel from one end of the wire to the other and move in the same direction. As I mentioned, their direction does not change. Another point about direct current is that the voltage in a direct or DC circuit must be constant, or at least relatively constant, so that the current can flow in one direction. Therefore, the voltage we consider in something like a flashlight battery is 1.5 volts. This flashlight battery provides a constant 1.5 volts. For the positive terminal of the battery, I refer you back to the previous session where I talked about voltage. Please review that a bit. The topic and the few sentences I'm about to share with you are related to that, and it will help you better understand what I mean. The positive terminal of the battery is always positive relative to the negative terminal. This is related to the fact that it depends on which reference point or position we are measuring the voltage from. We said that voltage can be both positive and negative. This refers to that concept. And if the negative terminal of the battery is measured relative to the positive terminal, then the voltage is negative. This constancy is what pushes the electrons in a single direction. That is, whether we consider it from positive to negative or from negative to positive, it's in one direction and there is no change in between. This was a brief definition of direct current. Now, the other common type of current that exists, and the one we deal with more often, even in our daily lives, is alternating current, which is abbreviated as AC. AC stands for alternating current, and we know it as alternating current or AC. In an alternating current circuit, the voltage periodically reverses itself. What does that mean? You'll understand better what this means in the following diagram, but for now, imagine that within a certain period of time, these electrons move to the right, and then again within that same period, let's say, for example, 1 second. These are all just examples. In 1 second, as it's moving to the right, then in the next second, it moves from the right back to the left, or returns to its original point. In other words, it moves back and forth and doesn't stay in one direction like direct current, which only flows in a single direction. The alternating current, so to speak, moves back and forth, or in other words, it doesn't move in just one direction at a single point. And when the voltage reverses, naturally the direction of the current also changes. For example, imagine we have a voltage going from positive to negative, and then this voltage changes again. It goes from negative to positive, and this causes the direction of the current to change. Why? Because, as we said, voltage is a force applied to electrons, and if the direction of this force changes, naturally the direction in which the force is applied to the electrons will also change. The most common form of alternating current, which is used in power distribution systems all over the world, has a voltage that alternates 50 or 60 times per second, depending on the country. That is, in Iran, we can say that since we have a voltage of 220 volts, the process related to the reversal of voltage happens 50 times per second. But, well, let's suppose when we turn on a lamp at home, we feel like the lamp is constantly on, and you might think that, well, this is a direct current. But if we use certain devices that can display this voltage change for us a bit more slowly, we realize that the light the lamp emits. Now, I'll also show you an animation about this in a moment. 50 times per second, given that we have a voltage of 220 volts. In Iran, this lamp appears to turn on and off approximately 50 times per second. But our eyes don't perceive the brief pause that inherently exists between turning on and off, and we consequently think that the light is continuously emitted and appears to be perfectly continuous. Alternating current is used in almost all power distribution systems around the world. The simple reason is that alternating current, or AC, is more efficient for us when it's transmitted over long distances through wires. That is, if we want to transmit AC, just see how much constant and strong force would have to be applied for us to have that electricity in direct current. But in terms of being economically viable and making our work easier, AC current is definitely more beneficial for us because these forces are applied over a period of time, and as we say, it's simply more efficient. On the other hand, all electric currents lose their power when they flow over long distances. Now, what is power? I'll explain this in future sessions, and as I mentioned before, to better understand the concept of voltage, we also need to know the concept of power. But the point is that AC circuits lose much less power compared to DC circuits. Keep this point in mind. Why, for example, what is power anyway, and so on, until we get to it in the next session. But this very advantage makes us give more importance to AC, and it becomes more beneficial for us. Well, here we have a schematic of AC and DC current. On the left side of the diagram, there is DC current, and as you can see, if we consider a simple circuit with a battery, the electrons are moving. If you look closely at the left side, you'll see that they are moving in one direction, which we call the clockwise direction. In this diagram, of course, in the direction of the clock's hands, these electrons, which are shown as dark circles, are moving, and there is no change in their direction. They keep moving in the same direction. But in the diagram on the right, which represents AC current, if you pay attention, within a certain time interval, the electrons move in the clockwise direction and then return and, so to speak, move in the counterclockwise direction. That is, in DC, notice that it moves like this. I'll show it like this, and in an alternating current within a certain specific time interval, at first it moves in this particular direction, and then it completely changes its direction again and proceeds to go like this. So this is what is meant by the voltage reversing, which causes the current to reverse as well. One point about AC circuits that I should mention is that the electrons in an AC circuit don't actually move along with the electric current. That is, for example, we can't say that they move to the right and then move back to the left. In fact, we can say that the electrons move back and forth in their own positions. That is, each individual electron moves forward and backward. It's not like a current where, for example, 10 electrons all move to the right over a certain distance and then 10 electrons move to the left over a distance. No, each of those electrons moves back and forth in its own position relative to this central point. For example, imagine here that this is a central point, and the atom itself and the electron move toward this side and then move back to the other side. That is, each of these electrons moves to the left and right. Focus your attention on this image for just a few seconds and you'll truly understand what the fundamental difference between AC and DC is in essence. So in AC current, the electrons don't move in a specific direction and are mostly just spinning around themselves. And if you remember a few minutes ago, I mentioned that in Iran, where the voltage is 220 volts, this back and forth movement happens 50 times per second. And during these precisely 50 times per second, each of these individual electrons moves back and forth in its own specific position 50 times. Or in other words, they effectively spin in place 50 times per second. And the net effect is that the electrons don't actually go anywhere. In their own place, they move back and forth or in a rotational, oscillating manner. We can say they move back and forth, or we can say they move like this and like that, relative to this central point that exists. Well, here we're also talking about the lamp, where if we consider a simple circuit that's connected to a battery and also has a lamp. On the left side, this is an example of a DC circuit, or in other words, our direct current. You can see that the electrons move continuously and the lamp here stays constantly lit. But in this part, which is AC and has alternating current, here you can see that the lamp is constantly turning on and off. We can see here that it keeps turning on and off, but this switching happens so quickly that our eyes can't perceive it. But by using certain devices and detectors, we can observe this continuous switching on and off. Sometimes, if you remember old mobile phones that had cameras, if you have one available, if you point it towards the lights and record a short video, or even if you don't save the video, you can almost sense this pulsing, that the lamp is turning on and off with a pulse. In this way, you can also understand what the AC current is like. Now, to give you a much better and more comprehensive understanding of alternating current, here I'll share a few truly interesting and important facts about alternating current, so you can grasp the fundamental concept of AC much more clearly and thoroughly. So here, I've brought a fascinating device commonly known as Newton's cradle, and I want to use it to clearly show you how alternating electrical current truly works. This device is sometimes also called the Newton's cradle toy, but we generally refer to it as Newton's cradle. As you can see, it consists of several balls that are suspended using a set of strings. You see, these balls aren't stuck together, but thanks to these strings, they're aligned in a single direction and are in contact with each other in a straight line. If I take one of these balls here and pull it away from this path and let it go, watch how it moves. The spherical object that I initially released here, allow me to firmly hold it for a moment, and then I will carefully let it go. Please direct your full attention to the ball positioned on the right side. It appears as though it is being forcefully struck, and consequently, that particular ball also moves significantly upward into the air. The ball on the right then comes back again, and this motion keeps repeating. See, like this? And the more I increase this distance, you can see that the ball on the other side rises by the same amount and then comes back again. Of course, if this device were made with much greater precision, this back and forth oscillating motion would continue for a much longer time. For example, if I let this go now, you'll see that this back and forth motion continues for a while and gradually decreases. But if it were made with much greater precision and friction, and similar issues were minimized as much as possible, this back and forth motion would last even longer. Now, for example, if I hit it from this side as well, you can see that the balls move in this way. But now, what is this device trying to show us? Alternating current works in almost the same way. At first, electrons move in one direction, but then they reverse their direction. They move in the other direction. For example, imagine the electrons are these balls. They move to the right, and then they move back to the left again. This back and forth movement of electrons in the circuit continues as long as the voltage reverses. It's the same idea of voltage going from negative to positive and positive to negative. So as long as our voltage keeps changing, the electrons will move accordingly. But as soon as the direction changes, or in other words reverses, the electrons also reverse their direction. The reversal of voltage in a typical alternating current circuit doesn't happen instantly. It doesn't happen all of a sudden. Instead, the voltage gradually oscillates from one pole to the other. So we can say that the voltage in an AC circuit is constantly changing. It starts from 0. It increases a bit, rising in the positive direction. When it reaches its maximum, it starts to decrease again. It comes back towards 0, and at that point it increases again, this time increasing in the negative direction until it reaches the negative extreme. Then, as it hits its maximum negative voltage, it decreases again, returns to 0, and this cycle keeps repeating. And with the diagram I have here right now, you can clearly see what I mean. It has what is called a sinusoidal motion. That is, if I consider the voltage, it starts from 0, makes a curve upward, comes back to the axis, goes below the axis, and then returns to the axis again. If you search for a sine wave on the internet or look at this diagram or this GIF here, you'll see that its pattern is like this, and AC voltage basically behaves like a wave. The positive and negative parts you see are just the voltage alternating. The fact that the voltage value in an AC circuit is always changing is actually very useful for us. But when it comes to DC, if I want to show it with a diagram or a graph, you can see that the part below this graph, the negative part, comes up to the positive side. In other words, in DC, it always moves in one direction, the positive direction, and its direction doesn't change. That's why it's called direct current or DC. But with AC, it goes up and down like this. Now, to get a closer look at alternating current, as I mentioned in future lessons, we'll get more familiar with it and this topic will become clearer for you. In this session, we just gave a brief introduction about direct and alternating current to see exactly what they are, and I also used Newton's cradle to give you another visualization so you can understand what is meant by alternating current. In this particular way, the electrons first move from the right side to the left side, and then subsequently from the left side back to the right side. This continuous back and forth flow that you can clearly observe here exists as a fundamental principle, and this phenomenon is a very concrete and illustrative example of what is known as alternating current. Well, this session, which was about comparing direct and alternating current, has come to an end. We would appreciate it if you share any thoughts or feedback you have on this topic with us. We hope this session has been useful for you as well. Until the next session, goodbye.